So now we're going to look at a heating curve problem that includes both change in temp and change in state. So to look at this, we are going to look at this example and kind of go through it. So it says, consider you have 20 grams of ice at a -10. It's heated in a closed container until it reaches steam at 130 degrees Celsius. Draw the temperature versus time, describe what's happening at each level. So we're going to draw this out first. So we're going to say, here's my 0. So first I have to warm this up to 0. It's down here at a -10. I got to warm it. Then I have to change the state. And I'm going to have to warm again. This is about 100. So we're talking about water. Change in state, and then I'm going to warm again for the last part, about 130. Okay? So we're going to make this segments. This is going to be segment 1, 2, 3, 4, and 5. So we're going to go down below and we're going to look at this. So looking at these segments, we want a microscopic description for each one of them. Well, at the first part, I have ice, and it is frozen and fused together like this, right? Wait a minute, let me do that again. Here's my picture, frozen together, okay? If I went to a macroscopic description, isn't there a change in temp for that first segment right here? You can see that there's a slope on the line. Now, for the next one, segment 2, I have a change in state. This is where melting is happening. Oh, so this is going to start to flow, and some of it's going to be melting. Okay. The next one is another change in temp. Oh, that means these particles are going to start moving faster. We know these particles are moving here, but be very slow. Okay. These still are flowing, they're still liquid. And then the next one, this would be a change in state. And the same temperature, now they're going to be and then the last one, I have a change in temp again. So now I'm going to have that really moving over. Okay. So you can see there's segments 1, 3, and 5. I have a change in temperature. That means I'm going to use my equation Q equals M C sub P change in T. Okay. At segments 2 and 4, I'm going to use the one Q equals M change in fusion or change in vaporization, depending on what's happening where. Another thing we can look at this, the slope on this graph is positive. It's absorbing energy all the time, right? So my answer should end up being a positive value. So in this part, energy is absorbed. And since it's absorbed there, isn't it causing greater movement? Here, energy is absorbed, and it's weakening attractions as it's changing in state. Those are my vectors on here. So this one absorbed again. So this is going to be energy is giving greater movement. Same thing, it's absorbed here, but this one is still weakening attractions. And it's still being absorbed here, except this one, this is giving the greatest movement. So that brings us to our equations that we use. So this one, since energy is being absorbed, it's Q equals M C sub P for ice. So we'd have to remember that, times the change in temp. And I would have to give you those specific heats. For this one, it would be Q equals mass times the change in fusion for the substance. Change in temp again, mass times the C sub P, and this time it's water, it's a liquid, times the change in temp. This one, change in state, equals mass times the heat of vaporization. And the last one is Q equals mass times the C sub P, and you have to use it for steam, times the change in T. Okay, so those are our equations. We really have two equations. You just have to recognize if you're going to use change in fusion or change in vaporization. Okay, so they want to know, find the energy required to do this. So we need to take each segment individually and calculate that and then sum those up. So I'm going to change this a little bit. Let's make this 20 with the dot decimal behind it and 10, and then we got 2 sig figs in our answer. Okay, now there's a couple other values I have to give you here, and that would be, what is the specific heat for ice? It is this. The specific heat of ice is 2.10 joules per gram. We know the specific heat for water is that 4.18 joules per gram times degrees Celsius on there too. And then we need the specific heat for steam. That equals 2.08 joules per gram times degrees Celsius. Okay, and then our heat of fusion and heat of vaporizations were given for us in other problems, and we'll just break those up as we do these. So if I was to go through and do this problem, I'm going to break these up into segments. So segment 1, it looks like I have Q equals mass times the specific heat times the change in temperature. So my mass is 20 grams times the specific heat, so I got to use it for ice, is 2.10 joules per gram times degrees Celsius times the change in temperature. It's 0 minus a negative 10 degrees Celsius. Calculate that. I got 420 joules. For segment 2, now I have the ice warmed up, it's going to melt. So it's Q equals the mass times the change in H, and it's going to be fusion because we're changing from a solid to a liquid. Well, the mass that I have is staying constant. And then I have to go, what is the change in H fusion, the enthalpy for ice? Wasn't that 333 joules per gram? So to calculate that, I got 6,660 joules. The third segment, now we're warming up that water. We're going to make sure this is water, and the change in temp to its boiling point. So we have the same mass, 20 grams. The specific heat of water is 4.18 joules per gram times degrees Celsius. And the change in temperature, it's at 0 and it's going to go to 100 to its boiling point. Calculate that out. I got 8,360. The next segment is when we're changing this water into a vapor. So it's the fourth segment. Equation is Q equals mass times the change in H for vaporization, or the enthalpy. So it's still 20 grams. And the change in H for this of vaporization is 2,260 joules per gram. calculation was 45,200 joules. And then the last segment is I want to take that steam and warm it. So that's mass times the specific heat of steam times the change in temp. Mass is staying constant. Always heating the same, adding energy to the same amount. The specific heat we said for steam was 2.08 joules per gram times degrees Celsius. And then the change in temp is from 100 to 130. Calculating that out, to heat that up, it's going to take 1,248 joules. Next, I sum those up. When I sum those up, I got 61,800 joules. If I went to sig figs, it'd be 62,000 joules. That would be my answer to it. It has to absorb that much to go through all of those changes in temperatures and changes in state. If you look at this, we were always using the same mass. We're doing different things to it. We're changing the temp, changing the state. Notice this one right here, when you change it into a gas and you break apart all of those attractions, that takes the most energy. I believe on the next page there is a question about that. So you can see when you break a substance apart and get rid of all of the attractions between the particles, it would take a large amount of energy. I'll leave you to answer that. I want to look at this last problem right here. This one, it says find the heat released, and let's change this 40 to with the decimal behind it. If you did this one, so we're releasing, so that means my answer should be negative because heat is leaving the system. So I'm going to just sketch the graph. I'm not going to do it, but I'll tell you what the answer is. So it looks like I'm at 115, and I'm going to cool it until it gets to 100, right? Because that's where it would change in state. Whoops, I did that wrong. So I'm at 115, and I need to, yes, I do need to cool it to 100 first. And then I'm going to have to change in state, and then I have to cool it again down to about 40. If you notice here, my slope is negative. Well, that should be telling me this. When I add these all up, it should be negative. Okay, so you're going to have to go through and calculate that and see what you get. I got, when I went to sig figs here, my answer was a negative 76,000 joules. See if you get that answer. You have 3 different segments to this. So you have segment 1, 2, and 3. Watch your change in temps and watch what you should use for specific heat for the substance. Is it a solid, a liquid, or a gas?